So welcome back. This is the second video for variable elimination algorithm, and in this video we're going to discuss this algorithm using the multiplication and summation operations that we defined before. So we know that if you want to compute the joint probability distribution for a network, we have to use the chain rule for the Bayesian networks. If we look just for one assignment, the chain rule has this form here, right? So we take values for the variables that we have. So let's use as an example this network here, and in this case we have the variables A, B, C, D, and E. So we take one assignment for these variables and we multiply the conditional probabilities that we have in each node. So for instance, we're going to multiply the probability of E given C. So that corresponds to this node here. We know that E has a parent C. So this is the same thing as the probability of E given C. So it's going to be a number, and we multiply this number by the probability of D given BC, and so on, until we multiply for all the nodes that we have in the Bayesian network. We can do that in a slightly different way, thinking about multiplying the tables instead of multiplying numbers. In this case, we're going to take an entire table that represents all possible assignments for the variables E and C and multiply by another table that has all possible assignments for the variables D, B, and C, and so on. So we are multiplying the factors. The end results are going to be the same. Here, in the first form, we'll have to iterate over all possible assignments for the variables that we have in the Bayesian network. In the second case, we have already the table. We're going to just multiply those tables, and the multiplication will take care of doing the multiplications in a correct way. But at the end, we will multiply all possible assignments in the same form. So when we multiply all those tables, the final result is going to be the joint distribution over all variables that we have in the Bayesian network. And let's suppose that you want to compute the marginal for variables D and E. So what we do, we multiply all the factors together and we sum out variables A, B, and C, and we're going to stay with the marginal for variables D and E. So it's going to be a combination of marginalization and multiplication. So we have the multiplication of the factors here. We have the summation marginalization of the variables A, B, and C in this part, and at the end we get the correct results. The problem of this approach is the fact that when we multiply all those factors together, we get the joint distribution over all variables, and that is exponential in the number of variables. So we still have the problem of complexity, but we can do better. We can anticipate the summations a little bit, so we never get into the full joint distribution. Let's see how we can do that. So in order to do better, we can use a very simple idea. So what we are doing, let's suppose that we have two factors, f1 and f2. And what we are doing is this. We are multiplying f1 by f2, and if we want to eliminate a variable x, we do the summation after the multiplication. But let's suppose that only factor f2 mentions the variable x. So in this case, we can anticipate the summation. So we can move the summation to this part here, and we can do this. We first eliminate the variable x in f2, and later on we multiply by f1. So in a more general case, if we have n factors, but only one of these factors, fn, mentions a variable, let's suppose that's x, we can move the summation forward here. So we move it to here. So we anticipate the elimination of variable x. So we're going to first eliminate x, and later on we multiply by the remaining factors. And if in the case that the variable x is mentioned in more than one factor, we just have to take care to first multiply all the factors that mention variable x, and after that eliminate the variable. Let's suppose that the variable x is mentioned in the factor fn-1 and fn. So what we do, we, instead of first multiplying all the factors and eliminating the variable x after that, we eliminated the variable x just after we multiply the factors fn minus 1 and fn. So we anticipated the elimination of a variable x. Just keep in mind that this rule is going to work, but we must be careful to multiply all the factors that mention a variable first and later on eliminate that variable. So let's use one example to make these computations more concrete. So let's take a very simple example where we have this Bayesian network here, just 3 nodes in a sequence A, B, and C. So if you have these 3 nodes, we need to have the probability of A is going to be a prior because A has no parents. We have the probability of B given A that is showing here, and we have the probability of C given B that is shown here. So we have these 3 factors that we want to multiply then and eliminate some variables. So let's suppose that we want to compute the P of C. So it's going to be just this marginal C. And we can see in the Bayesian network in the parameters that we don't have this information readily available. All that we have that mentions C is actually a conditional probability distribution, probability of C given B. So we needed to do a little bit of inference in order to get P of C. What we have to do, eliminate the remaining variables. So we have variables A, B, and C. We need to eliminate the variables A and B in order to stay with the variable C. So let's do that. So we first have to decide what's going to be the order of elimination. So we can eliminate A and B or B and A, and that may impact the performance of the algorithm. So let's suppose that let's do it in a very simple way for now. Let's suppose that we're going to eliminate the variables A and first and B later. So if you want to eliminate the variable A, the first thing that we have to do is to look at all factors that we have and multiply all the factors that mention variable A. So if we look here, we have these 3 factors, and the factors that mention variable A are these 2 here. So the probability of A and the probability of A given B, the probability of B given A. So we have these 2 factors, and we needed to join them first and eliminate the variable A. To make the join is the multiplication operation that we have already discussed. What we have to do, we're going to create a new factor. And this new factor will have all the variables that mention the variables that you have in these 2 factors. So all the variables are just variables A and B. Okay, because here we have variable A, and here we have variable A and B. So the resultant factor will have the variables A and B, the union of the variables of each factor. So what we have to do is carefully multiply the entries in order to obtain this new table here. So we have this assignment, A true, B true. What I'm going to do, go here where we have A true and go in this row here where we have A true and B true and multiply these 2 numbers. 0.6 times 0.9 equals to 0.54. And we keep doing that. So here we have A true, B false. So again, we take A true, but now we need to take this row over here, that's A true and B false, and multiply. It's going to be 0.6 times 0.1, 0.06. Keeping doing that. Now we have not A and B. So now we're going to take this guy here, not A, times not A and B. That's the matching one. So it's going to be 0.4 times 0.2, 0.08. And finally, not A, not B. Again, we take the not A here and not A, not B here. It's going to be 0.4 times 0.8, 0.32. So now we can forget about these 2 factors here because we have already multiplied them and we have the resulting factor. So the 2 factors that are of our interest now are this new factor that has the join and this factor here that still have the information about B and C. We see now that we have one factor, the new one, that mentions variables A and B, and we have also this other factor here that mentions variable B and C. and so A is just mentioned in this factor. We can eliminate A. To eliminate A, what we have to do is the summation process. So it's also very simple. Sorry about that. It's also very simple. It is what we have to do. We have to eliminate the variable A. So this variable here is going to disappear. So we will take all the assignments that we have for B, and we're going to sum the entries that have this assignment. So for instance, we have here B and B true. Okay, we're going to have a new row here that has B true, and we're going to sum all the entries in which B is true. For that, we're going to operate over the variable A here and sum over all possible assignments of A. In the case A is also binary, so it's going to be A true and A false. So the result is 0.54 plus 0.08, 0.62. The same thing we're going to do for B false. So we take all the assignments that we have B false here, all the entries we have B false, and we're going to operate over all possible values of the variable A true and A false. It's going to be 0.06 plus 0.32 equals to 0.38. Now we have this new factor here. We can forget about this one, and we will operate over these two factors. Notice that we do not mention variable A anymore. All we have is one factor that mentions B, the other one that mentions B and C. We want to eliminate B, so before eliminating B, we needed to multiply those two factors, and we will get it to make another variable elimination. Okay, now we're going to repeat the process once again, but now for the elimination of a variable B. So these are the two factors that are still remaining. And we know that both mentions variable B, so we have to multiply them first and eliminate variable B afterwards. The process is the same. When we multiply these two factors, we needed to get a new factor that mentions all the variables that were mentioned in the two factors. So we have one variable over B, one factor over B, another factor over B and C. The resulting factor will be over B and C. And the multiplication process is the same that we described before. For instance, for this entry here, where B and C are true, we're going to multiply this entry here, where B is true, and this entry here, where B and C are true. So it's going to be 0.62 times 0.3. The result is going to be 0.186. And we keep doing that for all the entries that we have in the joint factor. After that, we needed to eliminate the variable B. We see that after we have a multiply, we can forget about these two factors here. We're not going to use them anymore. We will look at the variable B. This is the only factor that we have. So it mentions variable B. We need to eliminate that. For doing that, the process is the same as we described it before. What we do, we look for entries of the variable C. They are the same, and we iterate over all possible values of variable B. So you're going to sum these two numbers here, and the sum of these two numbers will be this number here. And we do the same thing for not C, and we're going to sum these two numbers, and the sum here will be this value here. All right, so now we have the factor that is the response for our inference. We have a factor that only mentions variable C, and for C true, we have the value 0.376. For not C, we have the value 0.624. We see that with the sum, it's going to be 1, so this is a distribution, and exactly the results that we are looking for. So this is the probability of the variable C, and we got our response. So here we have our first algorithm for variable elimination, and it's basically the process that we have just described. So we will take as input the Bayesian network N. We're going to take the query variables Q. Look here that Q is in boldface, indicated that is a set of variables. So we can ask for the prior marginals for one variable, for two variables, or more variables. It's up to us. And we have a variable ordering that's pi, that will say to us what is the order that I'm going to eliminate the variables. That ordering is important, and the different orderings will result in different complexities. So it's important for us to understand that and see how we can set a good ordering in order to make the algorithm more efficient, but we're going to see that later. We're going to return as a result the prior marginal probability of Q. So we start with a set S that is all CPTs that we have in the network, in the Bayesian network N. And we're going to iterate through the variable ordering pi and take one variable at a time. So that is this for loop here. For each iteration of the for loop, I'm going to take all the factors that mention the variable pi I. So in the first iteration of the loop, I'm going to take the first variable in the elimination order. I'm going to take all the factors that mention that variable and I'm going to multiply them together and have as a result a new factor f. We're going to eliminate the variable pi I of this new factor and get this new factor fi. And now is the time for eliminating all the factors that we had before that we call fk. These are the factors that mention the variable pi I, so we can remove them from S and include a new factor fi, the set S. So we are replacing all the factors that we multiplied by a new factor fi. So we keep on doing that for all the variables that we have in the ordering pi until we get to the final variable. And when we finish that, we will have a small set of factors that we need to multiply them together. This small set of factors are the factors that mention the variables in Q, our query. So we multiply those factors together and return that to the user. And a simple way to try to understand how much work this algorithm is doing is to look at the ordering that we are processing and take a look at the size of the factors that are being created by the elimination order. So if you look at this ordering here, pi equal A first and then B, you're going to see that when we eliminate the variable A, we'll have to multiply these two factors together. So we're going to create a factor that has two variables, but after we eliminated the variable A, this factor will have one variable. So what we are showing here is that the resulting factor after the elimination of A has just one variable, that is variable B. And we take this new factor that has only variable B and we multiply by this factor and later on eliminate the variable B. So in this case, again, we have as we do the multiplication, we will have a factor over two variables that are going to be B and C, but after we eliminated variable B, we will have a factor over just one single variable. So the size of the factor is going to be 1. So if you look at the ordering A, then B, we can say that the largest factor that we created after the elimination of the variables were factors of size 1. If we look at this elimination order here, we're going to first eliminate B, then A. So we first need to take all the factors that mention B, and these are the two factors that mention B. We need to multiply them. But now we'll have a resulting factor that mentions variables A, B, and C. After we eliminate the variable B, okay, there is a typo here. After we eliminate the variable B, we will have a resulting factor that mentions variable A and C. So that's why we have these two here indicating this factor over two variables. And we will multiply by the factor that mentions variable A because we needed to eliminate the variable A. So we multiply this resulting factor by the factor A. They're going to mention variables A and C. We eliminate A, and the resulting factor has just one variable, that is variable A. So we can see that in this process here, the largest factor that we created after eliminating the variables has size 1, and in this one here, the largest one has size 2. So the second one the elimination order B then A is less efficient than the elimination order A and B. You may say, okay, I got this, but I think that it would be better to, instead of counting the number of variables that we have in the largest factor after the elimination, we do that before the elimination. But okay, that's fine. Just remember that we are talking by the difference of 1, because in each step of the elimination process, we eliminated one variable. So the factor that we got after the elimination of the variable is 1 less than the factor that we had before eliminating this variable. So the results will be the same if we're just talking about the difference of 1. So some books talk about the size of the factors before, and some talk about the size of the factors after the elimination of a variable. In this course, we will take the size of them after the elimination. One important observation is that any ordering will work. So we can choose any ordering that we want. What we are talking about is that some orderings are more efficient than other orderings. So it would be interesting to find what is going to be the best possible ordering in order to have the most efficient implementation of our algorithm. And we're going to address this later on. For now, we need to understand what is the complexity of this algorithm. And a simple way of thinking about it is that we have any variables. And that means that we have also any factors. So we have one factor per node. So we have one factor per variable. And the process that we are doing, we are taking all those factors that we have, and we are multiplying them and eliminating variables. So when we need to eliminate one variable, we take all the factors that mention that variable, we'll multiply them and eliminate what we had before and take this new factor, and keeping doing that. If we have any variables, because we just multiply each factor once, we will have any of these multiplications, and also because we have any variables and we're going to eliminate most of them, because usually we are interested in a factor that has a small number of variables, we can think that we also do any eliminations of variables. So we know that the cost of multiplying and eliminating a variable depends on the size of the factor. So we can think in terms of the worst case analysis that the cost will be any times the size of the largest factor that we may have. So we can think that if this largest factor has w variables, the complexity will be m times an exponential in w, right? So because we have w variables, but the number of entries in the table will be an exponential in w, so it will be n times exponential in w. So we call this number the width of the elimination order. It's frequently used as an indicative of the performance of the algorithm or the quality of the elimination order. And we want to find the elimination order that has the smallest width, right? So that is going to be the most efficient one. So it's the elimination order that will lead us to the smallest, largest factor that we can get. The complexity of the algorithm, so will be this factor, this component that we have just discussed, plus one extra component that is the final multiplication that we needed to do in order to get the final answer. So we eliminated the variables, but as we are interested in answering a query over a set of variables Q, at the end we may have a small number of factors that depend on how many variables we have in Q, that we need to multiply those factors together in order to have a final answer. So this final step will be just the multiplication, will not involve any elimination of variables, because we have already eliminated all the variables that we are not interested. So you just have the variables in the query Q, but we may have these in different factors that we need to put together. Actually, we have an option here. In some case, we'll in fact multiply those factors together and give as answer to the user a single factor that has all the variables in Q. Sometimes we are fine with returning to the user a factorized version of this distribution. So we give give to the user all the factors individually. Both options are possible in the case that we need to summarize all those factors in a single factor. We needed to make this multiplication, so we needed to account for this final term here. And okay, and if you want to measure the width of an elimination order, we can take the algorithm that we just described and modify it a little bit in order to do a process of a simulation of the elimination of the variables. So instead of doing the multiplication and the summation, we only look at the factors that we created during the process. So it's going to be a sort of a simulation process, and we will register what is the size of the larger factor that we created. So we can look at this process as the following. Let's suppose again that we have this Bayesian network here as an example, and we want to eliminate the variables in the order B, C, A, and D. So in the end, we'll have this marginal here over C. So these are the factors that we have, right? So they are here in the S. So the S set starts with all the factors that we have. And we want to eliminate B. Again, we're going to take all the factors that mention B. So we have this, and we have this factor here. We're going to multiply it, but actually we don't do it. We don't do the multiplication. We just register that we will take these two factors together, and we will have, as a result, a factor that mentions the variables A, B, C, and D. But after the elimination of the variable B, they're going to just mention A, C, and D. So we register that here, F1, the A, C, and D. And we note that F1 is the resulting factor that we multiply all the factors that mention B and eliminated the variable B. As F1 mentions three variables A, C, and D, we register that here, that is the size of the factor that we created. We continue in doing that. Now we're going to eliminate the variable C. We take all the factors that mention variable C. They're going to be these, and also the factor F1. We multiply all of them together and create a new factor F2. So the factor F2 will mention variable A, D, and E, and this is what we did, right? So factor F2 is the multiplication of this factor, and also factor F1. And so you're going to mention A, you're going to mention C, D, and E, but after the elimination of C, it will only mention A, D, and E. And again, we continue in doing that. We register that this new factor F2 is over three variables, and we continue doing the process. Looking at that, we are not actually doing the computations, right? So the heavy part of the computation is the multiplications and the summations, but we are not doing that. We are just registering what are the domains of each factor. So now we're going to multiply all factors that mention A. We have this factor here, and we also have F2 mentions A. So we multiply them together and eliminate the variable A. So we're going to create the factor F3. So the factor F3 is the multiplication of the factor that mentions A and also F2. We eliminate the variable A. We're going to keep the variables D and E. So I just noticed here that there is a type here, it should be D, right? So F2 is defined for variables A, D, and E, not A, C, and D, not A, C, and E. So again, we multiply these two factors and eliminate the variable A. We're going to have a factor F3 over D and E. And this new factor F3 mentions two variables that we register here. And finally, we only have the factor F3, and we need to eliminate the variable D. We do that. That's now we not involve any multiplications, just a summation, and we eliminate the variable D, and we have a resulting factor F4, and it only has variable E. So this final factor here has only one variable. And the width of this elimination order is going to be 3. That's the maximum number that we saw during the entire process of elimination of all the variables. So you may think, okay, that's a way of measuring the quality of an elimination ordering. So I could do that for all possible orderings that we have and choose the best one. The problem is that this approach is going to work for a small number of variables because we have n factorial possible elimination orders for any variables. So yeah, it's not going to be possible to test all the n factorial possible permutations of the variables. So this is not a feasible approach when you have a larger number of variables. But if you want to compute the quality of a few elimination orders, that it would be okay. Let's suppose that we have some way to select some of the elimination orders that you think they are good, and you want to measure the quality of these elimination orders, so we can use an approach like this one. Just remember that this approach is not doing the multiplication and the summations. In fact, they are just simulating this process and looking at the number of variables in each factor. All right, so that's good for now. Let's take a break and we'll continue in the next lecture with variable elimination algorithm.